Thank you. This is a joint work with my advisor, one of my advisors, Claire Monteleoni. And since I'm going to be talking about online clustering with experts, let me start from explaining the setting. So online means that we have infinite data, endless stream of data. So for instance, it can be internet transactions, environmental sensor data, satellite imagery data, weather measurements, prices, any data that is too large compared to computational resources so that it has to be accessed sequentially. We also have a fixed amount of memory. In case of supervised learning, we want to announce prediction at every time step. In case of unsupervised setting like clustering, we want to announce clustering at every time step. And computation or memory must not grow with time. So you can think of very many applications for this setting. For instance, topic detection, for instance, aggregation of online news stories, or some spatio-temporal problems in climate informatics, or solving some problems in streaming media. And clustering refers to a broad class of unsupervised learning tasks aimed at partitioning the data into groups. Clustering is widely used to summarize large quantities of data. Again, the example is aggregating online news stories, for instance. One way to evaluate clustering is to ask a human expert for judgment. But often we don't have a human expert. We want to eliminate the human expert from the loop. So with no assumptions on the data, no human expert, one way to evaluate clustering is to have some objective function. A widely cited and studied objective is a k-means clustering objective. In the Euclidean space, the way we compute it is we sum the squared distances between the data points and the closest cluster centers. It is well known that optimizing k-means objective is NP-hard, even when the number of clusters is equal to 2. And actually, very few algorithms approximate it. So let me explain what I mean by approximation. So if I have algorithm, clustering algorithm, that I claim is B approximate, where B is some constant. So if somebody will give me data X, any data, and my algorithm would cluster it, outputting clustering C, then I claim that the cost of my solution is upper bounded by B times the value of the optimum. We also can have AB approximation guarantees. So this is the setting where the algorithm is allowed to output A times K centers and still achieves this B approximation guarantees. So even the k-means algorithm, the Lloyd's algorithm, does not have an approximation guarantees with respect to the k-means objective. Few algorithms in batch setting has these approximations, even fewer in a streaming setting. And in the online setting, there is no algorithm that provably approximated. So our work addresses the open problem posed by Dasgupta to design an online algorithm for k-means clustering of endless streams in the following framework. So at time t, the algorithm is announcing a set of cluster centers CT and sees the data point XT and incurs the loss on this data point under the clustering CT. So this is computed by the squared distance between the point XT and the closest cluster center to point XT in the clustering CT. So the hope is that we can develop some reasonable bounds on regret, which is the difference between the cumulative loss of the algorithm and the optimum value of the k-means objective on the entire stream seen so far. We're going to slightly modify this framework. It's going to be apparent as I will proceed with the presentation, but this is the general problem we address. So our goal is to approximate the k-means clustering objective with an online clustering algorithm. What we're going to do is we're going to extend the online learning algorithm from the literature, from supervised learning, from the works of Herbster and Varmuth and Monteleoni and Diacola, to a clustering setting. So those algorithms then use the experts' advice, and they span a form of a distribution over the experts. And the way they update this distribution is by computing the prediction error. we don't make any predictions, so we're going to update it using the approximation to the k-means objective obtained so far. And then we're going to prove something that in the theory, in the literature, is called C-eta realizability of our clustering and loss function. And that will allow us to extend regret bounds from Herbster and Varmut and Monteleoni and Jacola to our setting. Finally, we're going to add assumptions on the experts. So we're going to assume that the expert are B-approximate batch clustering algorithms run on sliding windows. And that will finally lead us to novel online approximation bound with respect to the optimum for the entire stream. So this is the general recipe. So the setting is the following. We have no assumptions on the data, as in the standard online settings. And the observations can even be generated online by an adaptive adversary. So we're going to be extending the algorithm from the supervised literature. So in the supervised literature, we have some family of algorithms. We're going to extend them to obtain the family of online clustering algorithms. So let me explain what algorithms we are actually targeting. So we have a master algorithm. The master algorithm keeps the distribution over the experts. Traditionally, experts can be anything. So these are black boxes. They can depend upon one another. They can change in time. They don't even have to be good predictors in the supervised setting. And the distribution over the experts is updated at every time step and captures how well the experts performed recently. To handle the changing observations, the authors usually maintain the generalized hidden Markov model when the hidden state is the identity of the best expert. And different update rules for the distribution over the experts give rise to different online supervised algorithms. So I want to explain so that we can understand exactly how our setting is different. So at each time step, we don't want to predict the label for the currently seen data point xt. Instead, we want to take xt and assign it to the closest cluster center. So this is a fundamental difference. What we're gonna, so that is why we decided to update the distribution over the experts instead of using predictions errors, which we don't have. We use the approximation to the k-means objective as seen so far. To be more precise, we're going to show that there is a very simple analog of the pair loss prediction that exists in supervised setting. There exists a pair loss clustering that satisfies certain mathematical properties, and those and this will lead us directly to the approximation guarantees. So I said that there are different ways of updating the distribution over the experts. So let me show what updates are we going to be using. So there is a static expert update. So this is a setting where if you look at the generalized hidden Markov model, there is no dynamism in the hidden state. In other words, we don't want the identity of the best expert to change with time. So if you look at the regret bounds, the comparator to your cumulative, the loss of your algorithm is the loss of the best expert if the sequence was given to you in a hindsight. We also have a fixed share alpha update. So this is a setting where you allow the experts to share the portion of its weights. And this way, the dynamism in the hidden state of the generalized hidden Markov model can actually occur because you allow the identity of the best expert to change with time. This switching is, however, governed by the switching parameter alpha, as you can see here. So this P is like describing you the transition dynamics. And so, right, so actually these different updates corresponds to the different level of non-stationarity in the data. Okay, we also are going to extend learn alpha setting. So learn alpha setting is the following scenario. You don't know anything about your data. You don't know how non-stationary it is. So if you don't know, what you can do is you can have meta-experts, which are different fixture alpha algorithms run with a different value of the parameter alpha. And then you perform Bayesian updates to track the best fixture alpha algorithm. So in other words, you want to learn how non-stationary your data actually is. So here's the setting for online clustering with experts. So we have experts that at each time step are announcing the clustering to the master algorithm. The master algorithm takes these clusterings and takes its convex combination. The coefficients of this combination comes from the distribution over the experts, right? So these coefficients are just the P1, P2 up to Pn when n is the number of experts. So actually for our theoretical guarantees, we really only need the cluster center that is closest to the currently seen data point. So for now, we will allow the experts to filter their center so that they give to the master algorithm the center that is closest to the currently seen data point, and the master algorithm takes the convex combination of those centers. However, for the experimental section, I'm going to show something much stronger. So I'm going to show you not the loss, but actually the cost of our methods. So naturally, to compute the cost, you need all the remaining k-1 centers. So the master algorithm obviously can ask the best expert to output the remaining k-1 centers. The best expert, I mean the one that has the highest weight at time t. And now we have the loss of a center output by clustering algorithm defined the following. So this is the scaled square distance between the currently seen data point and the closest cluster center. Scaling only shrinks your word to the ball of radius 1, so you want your data to live in a ball of radius 1. I want to give some more intuition to why we have chosen this kind of loss. Well, in a batch setting, if you would compute the k-means cost, you just look at the entire data set and you square the distances between data points and the closest cluster centers. In the online setting, you can't do it. So in a way, the best you can do at time t is simply to look at your data point xt, find the closest cluster center in the current clustering, and just square the distance. So this is in a way like an online counterpart of the k-means cost if you were in a batch setting. Of course, this is not by any sense a formalist. This is just like an intuition. But this was our intuition for choosing this loss. So then we have proven the 2/1/2 realizability of a loss clustering pair. So this is nothing more than just a certain theoretical property, mathematical property, that links the loss with the log loss. And this is this inequality. It's quite important, actually, because if this inequality is satisfied, then you can prove certain interesting regret bounds that I'm showing here. So we are extending the regret bounds to the clustering setting. I will later on use these bounds to obtain the approximation guarantees with respect to the k-means objective. So let's take a look at what those bounds are. So the first two is the static expert bound and the fixed share alpha bound. On the left-hand side, you have the cumulative loss of your algorithm. On your right-hand side, you have the first term is either the cumulative loss of your best expert if the sequence was given to you in hindsight and regret. On the second bound, this is the loss of the best S partition. So what do I mean by the best S partition? I have a sequence. Somebody gave me a sequence, and I chop it into, I divide it into S pieces, and I just map each piece to the best expert. So right. So then N is the number of experts. H is the entropy, and the relative entropy. T is the length of the sequence seen so far. We also have fixture alpha bound and learn alpha bound when we actually have, instead of the cumulative loss of the algorithm, we have log loss. So this might be a little bit confusing, but I just want to assure you that for the approximation guarantees on the left-hand side, we're going to have everywhere the cumulative loss of the algorithm. So this is only just for the regret bounds. We have this log loss. Okay, so learn alpha bound is when you want to learn what's the level of non-stationarity in your data. So the way to do it is, as I said, you have meta-experts, which are fixture alpha algorithms run with different value of the parameter alpha, right? So you can actually discretize alpha and into M discretization levels. And actually in the literature there is a method to optimize this bound. So by optimizing, I mean that the second term can be shrunk to a constant. So roughly you can just upper bound this what is next to t minus 1 by some constant over t minus 1. But this is only provided that you know in advance what is going to be the length of your sequence. So then you want to, so then what we did is we instantiate the experts to be the approximate batch clustering algorithms run on a sliding window of size W, and we want the sliding window to contain the currently seen point xt. So naturally the doubt arises, okay, if I have xt in a window, then I can just trivially output xt as the cluster center closest to itself. I trivially minimize the loss, I'm done, right? Well, actually it's not true. So you can prove that no B-approximate clustering algorithm would trivially optimize the clustering loss function. So in other words, what we have shown is that if you have a B-approximate batch clustering algorithm, then if your algorithm will try to output xt as a cluster center, then there exists always a sequence such that it breaks the approximation assumption. And actually this is a pretty real life counter example, and the way you break the assumption is actually, it's very easily to break this assumption. So yeah, I can provide some intuition to the counter example later on. So we took the regret bounds and we played with the first term on the right hand side, and so it turns out that actually if you play with it, you can actually obtain the following approximation guarantees. So on the left hand side you have the cumulative loss of the algorithm, whereas on the right hand side you have the optimum value of the approximation to the optimum value of the k-means objective on the data seen so far. W is the size of the window. B comes from the fact that your experts are B approximate. R is the radius of the world in which our data lives. So I'm here presenting static expert bound, fixture alpha bound, fixture bound, fixture alpha bound, and learn alpha bound. Okay, so let me talk about the experiments. So we have done the experiments with the following data sets: the mixture of 25 well-separated Gaussian and some UCI data sets, like for instance cloud data sets, spam-based data set, forest fires, wall-following robot navigation data set, we call it just robot data set, and intrusion data set, KDD cap. Just want to mention that the robot seems to be the most non-stationary. We have used 6 clustering algorithms as experts. Actually, we have divided our experiments into 2 parts. So we have experiments with 3 experts, and then the experts are Lloyd algorithm, k-means plus, and heuristic called online k-means. The reason for this is they output k-centers, but we also wanted to experiment with more experts, so we also had experiments with 6 experts where we added the 3 variants of k-means sharp, but they can output different values of the parameter k, so that's why we do it separately. The window size was set to 200. You can tune the window size to tune the performance. We didn't really, we didn't do it, but we know it can be done. Okay, so here on the table I'm reporting the mean and the standard deviation of the k-means cost on the data seen so far. A1, A2, A3, A4, A5, and A6 are the experts. SE is the static expert. F1 to F5 are fixture alpha with, so F1 is the smallest value of the parameter alpha and then up to the highest value. We have learn alpha LA. And we compared with 2 algorithms in the literature, the online k-means and the doubling algorithm, very well-known algorithm. So from the table, what you can see is that in most cases, we perform better than with the methods we compared with. And also that if you don't know anything about your sequence, the best thing you can do is you can actually apply learn alpha that tracks the performance of the best fixture alpha algorithm. We also show the k-means cost on the entire sequence. So I emphasize this is everywhere cost, not loss. This is stronger. with respect to the number of cluster centers k. This orange, like brownish curves are the experts. So again, in most cases, at least one of our methods outperform all the others. The online k-means did better on one experiment. Also, sometimes the doubling algorithm does better, which is not the case for the robot data set, very non-stationary data set. Though I must emphasize that neither doubling algorithm nor online k-means were analyzed with respect to the k-means objective. Here we have the analogs to the learning curve. So this is the k-means cost on the sequence so far with respect to time. So this curve gave rise to the statistics shown in the table. Some interesting extra observations is that as you increase alpha, you have more fluctuations. But actually, learn alpha, which is this black curve, suffers less fluctuations than all the other algorithms. Like it's a little bit maybe more stable, though I just don't want to confuse with the notion of stability and clustering. I'm not sure if that's related. Anyway, so we believe that this is the first work providing regret bounds for online clustering in the case where the number of clusters is greater than 1. We present the novel online approximation guarantees with respect to the k-means clustering objective. And as experiments show, our algorithms exploit the performance advantages of the clustering algorithms used as experts. Thank you.
We have time for questions.
So intuitively one would expect that it's easier to approximate the best possible clustering if there is a good best possible clustering. Do you agree with that? And could you use that somehow?
You mean about the quality of experts?
I mean that clustering is particularly hard in the cases when there is no good clustering.
Well, yeah. So as I said in the very beginning, we have a non-stationary data set, and there's really no way in very many cases to evaluate the clustering. So really the best you can do is simply compute the k-means objective. I know that the perfect situation is if you have like human expert or that sees the data and you actually see this well-separated clusters, for instance, but in some cases you don't have it. You don't have a human expert, so you just have to use some kind of an objective. Sure.
So you answered the question which is a little bit different than the question that you asked. I mean, you wanted to get a guarantee compared to the optimal clustering.
Yeah.
You got guarantees compared to the best experts.
So actually
so if you have B approximate experts, then you can do it. But it's not clear to me how you get a B approximate expert in the online setting. I mean.
So you mean you don't exactly understand how I moved from regret bounds to the approximation guarantees? Oh, so yeah. So well, this is a little bit technical question because there's quite a lot of math behind it. But the intuition is the following. So in the regret bounds, I have this loss of the best expert. But so this is the sum of the loss at each time step. But at each time step, the loss of the expert is a component of the cost, and then you have a sliding windows. And actually, it turns out that if you look at the sliding windows, the k-means cost on the sliding windows, then you can from this you can actually obtain the approximation on the entire data stream. And the way you do it is actually, it turns out that I want to make sure not to like invert this. So we used a very simple property. Like if you have two windows, you compute optimum on this two, then it's actually upper bounded by this. And so this is used to obtain the, right, so this is used to go from sliding windows to the guarantees on the entire sequence. So this is an intuition, but there's quite a bit of math behind it, so.
Are there any more questions? I'm wondering how you determine the number of clusters in online way.
Yes. Yeah, so that's a good question. So, well, obviously for artificial data set, we have 25 well-separated Gaussians, so there's no challenge in setting the number of clusters. We just tried a few different settings. I don't think we have any intuition of how many clusters to see in a data. Like determining the number of clusters in your data, it's a challenging problem itself, so we didn't address it in this work. Though I agree with you that this is a very interesting problem.
I think we'll postpone for the sake of time to postpone other questions for the breaks.
Sure. I'll be available offline for additional questions.